In this example, we are given that a large mirror of length 5 cm is illuminated with a monochromatic light of wavelength 6000 angstrom from a narrow slit which is 1 mm above the plane of mirror and 5 cm from one edge of the mirror. And it is asking us to find the fringe width on a screen at a distance 120 cm from a slit. It is also asking us to find the width of interference pattern on a screen. We already studied about large mirror in previous sections that if this is the mirror, as per the given question, the length of the mirror is 5 cm and a slit is also given to us which is at a distance of 5 cm from one edge of the mirror and it is at a height of 1 mm above the plane of mirror and at a distance 120 cm from a slit. That means at a distance of 110 cm from this mirror, that is 120 from the slit, we have placed a screen where we are required to find the interference pattern. If the line of mirror incident on a screen at point O, this is the point of intersection of line of mirror on the screen, and we are required to find the region of interference here from this slit S. We can find out the rays from the edges of mirror and the field of view if this would have been an observer and it is looking into the mirror, or directly we can find out the region on a screen where its light is reaching directly as well as by reflection, because the light which is incident on the mirror and it is reflected, then it is reflected in such a way that these light rays appear to be coming from a point which is the image of the slit which is S prime. So this is the point we can consider as the other slit S prime from which the light is reaching over here. So if these points are point A and point B, then within this region light is directly reaching from the slit as well as after reflection. So this is the region of interference where fringes are obtained. If we are required to find this length AB, that we can easily do here. The value of AB we can write as OA minus OB, and OA and OB we can easily obtain by using similarity. In this situation here we can use this length is OB. If this angle I consider as theta, and for this triangle we can write this as OB by 110 centimeter. This must be equals to, here this is the angle theta, so here we can write this as 1 mm divided by this also, this angle is also theta, this divided by 10 centimeters, so this is 0.1 by 10. Which implies the value of OB we are getting is equals to, here the 0 gets cancelled out and there's 1.1 mm. Similarly, here in this triangle, if this angle is taken as phi and this also phi, here we can write with similarity of triangles OA divided by 115 is equals to, here this will be 0.1 divided by 5 centimeter, and if you simplify this, OA will be equals to this 11.5 by 5, that is 2.3 centimeter. Here this should be 1.1 centimeter, by mistake I have written it 1.1 centimeter, and if we substitute the values, this region of interference we are getting is 2.3 minus 1.1. and the region is 1.2 centimeter. That is the answer of this problem, where we are required to find the region of interference. We are also required to find the fringe width on the screen. So here in this equivalent setup of Young's double slit experiment, here we can use the value of a small d, that is the separation between the slits, that is 2 mm, that is 2 into 10 to the power minus 3 meter, and capital D, that is separation between the slit plane and the screen, which is given to us as 120 centimeter, that is 1.2 meter. And here we can directly write the expression of fringe width, which is given as beta is equals to lambda d by small d. On substituting the values here, we can see lambda is 6000 angstrom, that is 6 into 10 to the power minus 7. D is 1.2 divided by the slit separation, which is 2 into 10 to the power minus 3 meter. And on simplifying, we are getting this will be equals to 3.6 into 10 to the power minus 4 meter, or that can be written as 0.36 mm. That is the answer to this problem.